Vectors in physics. Vectors are a useful mathematical tool that shows up in a lot of physics in a lot of different ways. It's going to be fundamental to everything we do from here on out. Today we're going to talk primarily about kinematic vectors, so position, velocity, and acceleration. But you know, of course, there might be force vectors or momentum vectors. You've run into those in previous classes. There's also field vectors, such as electric or magnetic or gravitational fields. So there's current flow fields. There are many different kinds of vectors. It's very crucial. We haven't dealt with all of the mechanics of vectors. Specifically, while we know how to multiply a vector by a scalar, which is just to rescale the vector, we haven't talked about how to multiply vectors together, and that's because it's complicated, and I want to wait until we have actual physical applications that use that effectively. So we're going to hold off on those until later, and we're just going to focus on the kinematic things for now. The position vector of an object is a vector that points from the origin to the object and has a magnitude equal to the distance between the origin and the object. I hope this is a very natural definition of it. We usually define position vectors as R vector. That's unfortunate. R immediately makes you think of radius, and while you can kind of think that your distance from the origin is your instantaneous radius of the curve that you might be tracking out, it's not really great notation, and we're just kind of stuck with it. It also leads to the incredibly bizarre algebraic sentence that R vector is x hat plus y hat, and that's just strange. The displacement vector of an object between two moments is, exactly like before, the change in its position. In other words, delta R is R later minus R earlier. Just like before. No change there. We've just promoted it to vectorhood. To illustrate, we have Alice, and Alice moves along this kind of strange curved path and ends up over here. Her initial position vector starts at the origin and points to her initial position. We'll call that R1. And her final position vector starts at the origin and points to her final position R2. Notice how for position vectors, which are distances, this is nice. It's basically just a picture. Note that the displacement vector points from the earlier location to the later location. It's the difference between these two, and the way I would take R2 minus R1 would be to invert R1. So temporarily, let's put a ghost vector here. We would have minus, let's put a different color actually, minus R1, and then we would add them, the two new vectors. But notice that minus R1 plus R2 is already in tip-to-tail format, and therefore delta R would go like this. That's a lot of work, and you can shorthand it by saying, hey, wait, delta R will always point from R, the initial position, to the final position. We can see that, we can see that here, the equation got covered up a little bit, but that R later is R earlier plus R1, plus delta R. How come? Because if delta R is R2 minus R1, then algebraically we can just turn this around by adding plus R1 to both sides, and we end up with that R2 is R1 plus delta R. In other words, where you end up is where you started plus how much it changed, which is sort of a duh statement, but worth commenting on. Once we've defined displacement, it's pretty easy to define velocity. We define it exactly the same way, that the average velocity is just the change in position over the change in time, displacement over duration, just like before. And then we can extend this to instantaneous velocity by taking the same sort of limit, that we make the time steps very, very small, and we see if there's a limit of this. Of course, we're doing sort of vector stuff here, right? We're doing, which is, maybe you haven't taken vector calculus, and that's okay. Although, remember, if we had done this delta R as the sum of components and unit vectors, then really it's just a bunch of algebraic statements, because the derivative is linear across addition. So that when we take, when we have, let's put it this way, remember we have that R is x hat plus y hat, not great notation. So then dr dt, which is the velocity, well, it's the derivative of this whole side, but the derivative of a sum is the sum of the derivatives, so it's d dt of x hat plus d dt, d dt of y hat. but the unit vectors are constant, so they come outside. So now we have just dx dt x hat plus dy dt y hat, and we find that each component is just the derivative of the corresponding component. So that's kind of nice. The components of the velocity vector are the derivatives of the components of the position vector. This is because the unit vectors are considered constant. They are just indigestible algebraic objects. In more advanced math classes, they will talk about unit vectors that change from where you are, and then things get more complicated. That's the mathematical origin of things like the Coriolis force and the centripetal force. Of course, the speed v is still just the magnitude of the velocity, but you'll have to find it via some Pythagorean relation. That v is vx squared plus vy squared square rooted, because it's a magnitude of a vector quantity. All right, if we have a position plot, let's say a y versus t plot, we can still utilize all the things we had before, but we have to remember they apply only to that component of the velocity. So for example, a line still represents constant velocity, but only in that direction. To fully understand the motion, we'd need two plots, one for x and one for y. Sometimes instead we'll be given the trajectory, which is a more traditional xy plot that shows all the points through which the object passes, but conveys no time information on its own. An illustration. This object is traveling rightward and vertically. It has a constant horizontal velocity because the x component of it looks linear. In other words, we look here and we say, oh, x versus t looks like it's a line, and a line on a position plot is constant velocity. But it's accelerating vertically because the y versus t plot has curvature. Looks something like this. It can be more complicated, and then it gets a little harder to visualize. For instance, we might go over to this graph and we say at t equals 2, we have x of 3 and y of almost 0. So at t equals 2, I should be at x of, whoops, yeah, something like this. I got my plots badly here. And then I just take all those different moments and I construct my curve. Here's what that might look like if we were to illustrate its motion on time. You might see the little dot. All right, that's these things going from t equals 0 and going up and then down and then back a little bit, and so on. We can construct the velocity vector by noting that it's always proportional to the displacement and therefore points in the same direction as displacement, and so we can see what happens. So let's watch the thing go around, and here these purple dots are sort of what would happen if we projected the speed forward a few minutes. They go up and down because Desmos doesn't have a great line arrow facility. So what we're really doing is just taking small dt's and saying if I take the velocity at the moment that we pick, so let's pause for a moment. If we take this velocity, the speed at this moment, and we just find vx and vy, and then we project forward over some very small time steps, we more or less can see where the object would have gone if it had gone at constant velocity. So what we can see here, we can't take the velocity as the slope of the curve anymore because there's no time information on this graph. This is a y versus x curve, so the derivative is not ddt of something, so it's not velocity. But it turns out that the velocity vector is always still tangent to the trajectory curve. So there's still a relation to the tangent, although it's not the one that we had before. But at any given moment, the velocity vector points in the direction that is tangent to the curve, and that's always true for trajectories, in fact. Since the velocity vector changes as time goes on, it should be no surprise that we can define an acceleration vector as the time rate of change of that. That is, the average acceleration is still just delta v over delta t. We promote them both to vectors. And then, of course, we have the usual instantaneous definition, which is that the acceleration vector itself is the limit as delta t becomes small of delta v over delta t, or we'd write dv dt. So think about it. Does a constant speed imply that the acceleration is 0? This could be considered a trick question if you aren't reading carefully. If the speed is 0, then d dt of the speed is 0, so would a be 0? Pause and think about that for a second. No, you can still have an acceleration even if the speed is not changing, because the direction can be changing, and the acceleration is the change in the velocity. So if something is moving in this direction, oops, that's pretty bad. Something's moving at this direction, and then a moment later it's moving in that direction as fast. Nonetheless, the velocity vector has changed, so there's an acceleration. We'll see that best in, for instance, a trajectory which is circular, wherein the velocity is in blue, and the acceleration that comes from that velocity is in orange. And we can see something like this. This is a case of constant circular motion, uniform circular motion, and so we get the case that the velocity vector and the acceleration vector are perpendicular, and the acceleration vector points towards the center. The acceleration vector is just found by taking d dt of the velocity vectors. Move forward a step, figure out what the v's are, and do it. Even though that went kind of quickly, that really gives us everything we need about these three vectors. We can still say that each vector has it such that the components are still the derivatives of their appropriate bit. So for instance, if we have, as a reminder, if we have that the r vector is x in the x hat plus y in the y hat, then the velocity vector is d dt of the r vector, which ends up being dx dt in the x hat plus dy dt in the y hat. And then that gives us that the acceleration, which is the derivative of that, is now d dt of vx in the x hat and d dt of vy in the y hat, or second derivative of x with respect to time in the x hat plus second derivative of y with respect to time in the y hat. In other words, each component is still just the derivative of the appropriate component of the thing before, which is one of the advantages of the unit vector notation to begin with, and really means there isn't as much to worry about this. We still have things like if our acceleration vector points more or less-ish backward, so this is v and this is a, then this object will be slowing down. The part of the velocity vector that aligns with the acceleration vector tells you whether it gets faster or slower, and the part of the acceleration vector which is perpendicular to the velocity vector turns the velocity vector's direction.